Okay, let's play around with Dijkstra algorithm. First, what does Dijkstra algorithm do? It finds the shortest path from a single starting vertex to all the other vertices in the graph. You can also terminate after just reaching the target vertex. Note that Dijkstra applies to both directed and undirected graph, but the edge lengths are required to be non-negative. There are three main components for implementation: an array that stores the distance from vertex to the source, an array that stores the previous vertex along the shortest path, and a priority queue that uses the distance from the source as the key. Here are some key ideas to follow. We visit a vertex when we dequeue the vertex from priority queue. During the visit, we set the distance and the previous vertex permanently. We then explore its unvisited neighbors and add them to the priority queue or update their keys. Note that we only need to explore neighbors that haven't been visited yet. To build up some intuition, let's picture the following scenario. Suppose we just dequeue a vertex v from the priority queue and get path 1. Path 1 has length equal to z, and we can claim that it is the shortest path starting from the source ending at vertex v. How can we prove this? Suppose for the sake of contradiction that there exists another path, say path 2 to v, that is shorter than path 1. Say vertex x is the previous vertex to v along path 2. The edge from x to v has length y. The source is at the distance x from vertex x. So path 2 will have a total length equal to x plus y. By assumption, we know that x plus y is less than z. Also, since all the edges are negative, y is larger or equal to 0. Therefore, we get x smaller than 0. So, x must be enqueued or dequeued before v, and we will visit x and add path 2 to the priority queue before we dequeue path 1. Here we see a contradiction. Therefore, the invariant holds that path 1 must be the shortest path to v if we dequeue it from the priority queue first. Let's do a quick walkthrough of an example. I suggest that you work on a piece of paper by yourself first, then come back to check with the video. Here S is the source and T is the target. We have an array of distance, array of the previous vertex, and a priority queue Z3 components. In the beginning, the distance to all the vertices are initialized to be infinity. We first visit S and fill in the two arrays for S, which is set permanently to non-zero. Then we explore all the unvisited neighbors of S and add them to the priority queue. We then dequeue the one with minimum priority and fill in the entrant in the two arrays for that vertex permanently. Repeat the same process until there is no more vertex in the priority queue. We only explore neighbors that have not been visited yet, which are not red in the graph. Add or update the vertex in the priority queue. And finally, we can retrieve the path and the distance from the table we just built up. So here's the pseudocode. You may want to pause the video and look at it for a moment. There are two ways to implement decreasing the priority of a vertex. We can either use a special priority queue, which allows us to decrease the key of a value, or insert the same vertex multiple times whenever we encounter a shorter path to it. As for the overall running time, we have performed insertion or decreased priority at most v plus e time, the number of vertices plus edges. Each time takes omega log v time. We have also performed extract mean for v times. Each time takes omega log v. As a result, the overall running time is v plus e log v. In conclusion, Dijkstra algorithm can find the shortest path from a single source to all other vertices for graph with non-negative edge lengths in time omega v plus e log v. Thank you for watching.